If I asked you to name the tallest mountain on Earth, you'd probably have an answer ready right away. Most people point straight to Nepal's Mount Everest. It is the widely accepted standard answer in our geography books and documentaries. For decades, climbers have spent their lives, and sometimes lost them, trying to physically conquer this specific peak, solidifying its place in popular culture. But the accuracy of that answer depends entirely on how we define our terms. There is a strict difference between reaching the highest altitude above sea level and measuring a mountain's actual physical height from its base to its summit. We suffer from a sort of sea level bias. Because humans live on land, we instinctively use the ocean's surface as a universal starting line for measuring height. By treating the water's edge as a hard boundary, we've inadvertently cut off the lower halves of some massive geological formations. To see how that bias works in practice, we need to leave the freezing Himalayas and head to the tropical coastlines of Hawaii. This is where you'll find Mauna Kea and its twin, Mauna Loa. These are towering, highly active geological structures that dominate the islands. Yet, if you only look at their dry terrestrial features from the road, you are observing a fraction of their complete geological story. To find their actual bases, you have to leave the sunlight behind and plunge down into the Pacific abyss. The ocean acts as a giant blue curtain, hiding the true starting point of the planet's largest physical monuments. This animated chart shows Everest's actual physical structure. If you measure Mount Everest strictly from its base on the Tibetan Plateau up to its summit, the mountain itself is 4.6 kilometers tall. Now look at the Hawaiian Twins. The portion sitting above the water on dry land is actually shorter than Everest's physical height. But watch what happens when we drop the baseline down to the ocean floor. We find another 4.2 kilometers of solid mountain submerged in the dark. When you add that submerged depth to the height we see in the clouds, these twin volcanoes measure a whole 10.2 kilometers from top to bottom. Put them side by side on an even footing, and the contrast is clear. 10.2 kilometers next to 4.6. By simply measuring the rocks themselves, from the floor they sit on to the peaks they form, Everest is dwarfed. Our maps and record books are drawn by land-dwelling creatures, and they reflect a bias toward the dry surfaces we can easily access. If you were to drain away the water, the Earth becomes a continuous rocky sphere, defined by massive ridges and deep valleys. Looking at the planet this way forces us to rethink what a landmark actually is, and how we judge scale on a global level. The most massive structures on Earth aren't scraping the stratosphere where we can readily spot them. They are doing the heavy lifting in complete darkness, miles below the waves. Dropping our arbitrary sea level standard gives us a clearer picture of the planet's actual architecture. The trivia answers change, and our understanding of Earth aligns perfectly with the rocks themselves.